In this series, we explore competing models for what happened at or even before the Big Bang. In many of the models we've explored, the universe is seen as having always existed. But one scientist who takes the opposite view is Alex Vilenkin. In 1982, he published a paper showing how the universe might have spontaneously created itself from nothing. And what he means by nothing is not the quantum vacuum, as some have alleged, but a state where there is not even any space or time. What's more, this nucleation event wouldn't just lead to one universe being created. Vilenkin was one of the first scientists to argue that our universe is merely one of an infinite number of bubble universes. These are some of the most controversial claims in physics. So who better to explore them with but Alex Vilenkin himself?
I had a good math teacher who encouraged me to study mathematics and gave me some challenging problems. So that was very helpful. And in the elementary school, and then in high school I had a good physics teacher. I also had a friend who had similar interests, and we decided to study together the general theory of relativity. So that was a challenging project, and we had to learn a lot of math. We had some calculus at school, but we studied differential geometry, which was pretty advanced stuff. And we read a book, which was Eddington's Mathematical Theory of Relativity. And at the end of the book, we met every week to discuss what we learned. And at the end of the book, there was some discussion of cosmology, with discussion of the structure of the universe and the beginning of the universe. And I was amazed that people can learn anything about such matters. And so from then on, I couldn't imagine doing anything else.
In 1927, Werner Heisenberg published his classic paper on the uncertainty principle, which implies pairs of particles and antiparticles spontaneously appear from the vacuum.
According to quantum mechanics, vacuum is actually a scene of a lot of activity. If you look at small microscopic distance scales, particles pop in and out of existence, and they kind of live on borrowed energy. You can have electron and positron pop out, but then they have to disappear because energy conservation does not allow particles simply to come into existence. So they borrow a little energy from the vacuum, and then they have to disappear pretty promptly.
More than a decade before Vilenkin's paper, Edward Tryon proposed that the universe might be a vacuum fluctuation.
Ed Tryon had what seemed to be a weird idea that the whole universe could appear in that way, kind of as a vacuum fluctuation. You can picture it like you have an empty space, which you can kind of picture like a sheet of paper. And then you can imagine a bulge forming on this sheet of paper and taking the form of balloon and then eventually pinching off. And this will be a new closed universe. So the problem is that the universe is a lot more massive than electron and positron. So you would imagine that but you need the universe to exist for billions of years. But Tryon realized that there is no problem, because the energy of a closed universe is equal to zero, actually, because gravitational energy is negative and energy of matter is positive. And in the case of a closed universe, that is the universe which closes on itself, space closes on itself like the surface of a ball. For a closed universe, it's a mathematical fact that the total energy exactly adds up to zero. The gravitational energy compensates exactly the positive energy of matter. And so there was no problem. No conservation law forbids creating a closed universe from the vacuum. And Tryon told me actually how it happened that he came up with this idea. He was sitting in a seminar, and I'm not sure that the topic of the seminar was related to this, but he said that it came to him like a flash of light, that he kind of had this sudden realization. And when the speaker stopped to collect his thoughts, he just blurted out that maybe the universe is a quantum fluctuation. And everybody laughed because they thought that was a funny joke, but he was serious.
Tryon's proposal is that the universe came from a vacuum fluctuation. But one can still ask, where did the vacuum come from? In 1982, Vilenkin decided to address this issue in the context of inflationary cosmology, which implies a stupendous exponential growth spurt in the early universe. For more information on inflation, watch episode 4 of this series.
1982 was the year when the theory of inflation was kind of more or less completed. Alan Guth, who originated this idea, he likes to say that inflationary expansion can produce a big universe from almost nothing. All you need is a tiny piece of some high energy vacuum, which can then expand and produce a huge universe. You still need this initial piece, and so the picture to me seemed incomplete. So where did that thing come from? And so that bothered me, and I kind of kept thinking about what was the possible beginning of inflation, what could trigger this or produce this initial thing.
The trick to understanding Vilenkin's proposal is to think about something that is impossible in classical physics, but it is permitted in quantum physics. It's a process that is essential for the sun to shine: quantum tunneling.
So if you imagine, for example, that you want to get a can of Coke out of vending machine, you have to throw in a coin, and then the Coke comes out. It cannot come out otherwise because there is a wall. There is an energy barrier that prevents it from coming through. But according to quantum theory, there is a small probability for the can of Coke actually to spontaneously materialize outside of the vending machine. So of course, if you wait there for this to happen, you will have to wait much longer than the age of the universe. But there is a small probability. Such quantum tunneling events happen routinely on microscopic scales. For example, they are responsible for most radioactive decays, where a nucleus is forbidden classically to break up because there is an energy barrier, but quantum mechanically it happens through quantum tunneling. See how tunneling, what I call tunneling from nothing, is possible. Let us imagine we have a closed universe, right, which is has two ingredients. It has high energy vacuum of the kind that you need for to drive inflation. Inflation, I should say, is a rapid accelerated expansion of the universe, which is driven by this unusual stuff, which is called high energy vacuum, or sometimes false vacuum. And a remarkable thing about this vacuum is that it has a repulsive gravity. So when the universe is filled with this stuff, repulsive nature of gravity causes the universe to expand with acceleration. Also, the other ingredient is just ordinary matter. So we have this universe with these two ingredients. Now, let us imagine varying the radius of this universe. If we make the radius small, the density of matter will grow, and then the attractive gravity of matter will dominate, and the universe will collapse. If you increase the radius, the matter will be diluted, and the repulsive gravity of the vacuum will dominate, and the universe will inflate, expand with acceleration. Okay, now I wanted to start with a very small universe. So suppose I have a very small universe. Classically, it would collapse because of gravity. However, and there is an energy barrier between that and the large size of the universe that would make it inflate. But what I realized is that instead of collapsing, the universe can do something more interesting. It could tunnel to a larger radius. So it would be a quantum tunneling process. So the universe will tunnel to a larger radius and will start expanding. And then I asked myself how small this initial universe can be. So I looked at mathematically, I discovered that when I take the size of the initial universe to 0, the mathematical description of the whole thing simplifies greatly. And what I had was a mathematical description of a universe tunneling from a point to a finite radius and starting to inflate. So a point is no space at all. So basically this is no space, it's no matter. And the universe in this picture is created spontaneously from basically nothing. I write nothing in quotation marks because it's not kind of philosophical nothing, because we assume that the laws of quantum mechanics are there, somehow there. There is no space or time, and the universe tunnels from this timeless, spaceless state into existence. As it appears, the universe has a very small size, it's filled with this high energy vacuum, and it starts to inflate very rapidly. The mathematical picture that I had gives the probability for the universe to appear in different sizes and also filled with different kinds of high energy vacuum. And what I found was that the highest probability is for the largest energy vacuum and the smallest initial size. So the universe appears extremely tiny, but then the high energy of the vacuum and its repulsive gravity cause the universe to expand very fast, and so it doesn't stay small, it becomes huge in very tiny amount of time.
So how does Vilenkin's tunneling from nothing model differ from Tryon's vacuum fluctuation model?
It is different from Tryon's model in two regards. First, Tryon had a disadvantage that he didn't know about inflation. So he couldn't explain why, if the universe appears as a quantum fluctuation, then a small quantum fluctuation is much more probable than a large one. He assumed the pre-existing empty space, pre-existing vacuum, and it wasn't clear where that came from. The main difference is in the picture of tunneling from nothing, there is no space before that and no time. When we say nothing in this context, tunneling from nothing, we don't mean quantum vacuum. It's actually what Tryon meant. Here we have a state without space completely. So there is no vacuum. The laws of physics are assumed to be there, and that's a great mystery, where they come from and what determines which laws they should be.
Most cosmologists accept that in order to understand the origin of the universe, we need to combine the general theory of relativity with quantum mechanics into a theory of quantum gravity. But there is no agreement in the field about how to do this.
All quantum gravity theories are now still at a pretty rudimentary level of development. So you can use what is called semi-classical gravity, which is the approximation where things are almost classical, but for example, things like quantum tunneling can still be described. And in that regime, all these different theories are pretty much more or less the same. The differences come really at the true quantum gravitational level, where the nature of space-time actually may change, like in string theory, which says that space may have more dimensions, or maybe even the space and time themselves are kind of semi-classical concepts, and on a more microscopic level we have some different structure, so the space and time emerge when you go to sufficiently large scale. And the same is true of loop quantum gravity.
If the universe began from such a quantum nucleation event, then what would be the cause?
Many quantum mechanical processes do not require a cause. So, for example, if you have a radioactive atom, you know that it will decay, but you cannot tell when. There is a half-life time. For example, you can tell that in a year, the probability for this atom to decay is 50%. Then the year has passed, it didn't decay. The probability for it to decay the next year is still 50%. Eventually, it will decay. But if you ask why did it decay at that particular moment, there is no reason. There is no cause. So quantum mechanical processes like this are uncaused. And the spontaneous creation of the universe is of the same nature. So it doesn't require any cause.
While many physicists accept that a breakdown of causality occurs at the quantum level, there are different interpretations of quantum mechanics. So how does this impact on the nature of causality in quantum cosmology?
The only interpretation of quantum mechanics that appears to make sense in cosmology is the Everett's interpretation or many worlds interpretation. Because the other, for example, the so-called Copenhagen interpretation, this interpretation requires that there is an observer outside of the universe with some measuring device measuring the universe. In the case of the universe, we don't have such an observer. So the universe is a self-contained system. And I think many worlds interpretation is required here. In the Copenhagen interpretation, things are acausal simply because it's kind of built in the nature of interpretation. You have a wave function describing your atom, and then the wave function collapses in the course of measurement, resulting in some of the outcome probabilistically. And there is no cause how you choose these things, the outcomes. In the case of many worlds, there is no these collapses of wave function, and the wave function evolves deterministically. So in a sense, this is a deterministic interpretation of quantum mechanics. However, this wave function describes an ensemble of universes, and in different members of the ensemble in different universes, you get all possible outcomes of your measurement. Simply, you don't know which universe you are in. And which universe you end up in is also an acausal kind of process.
I've heard some people claim that there's one with a pilot wave theory or a de Broglie-Born, and that is causal. Do you have any comment on that?
I thought that this pilot theory is a beautiful idea. I looked at it in my youth, which was a very long time ago, and I didn't really follow it afterwards. It was, to my understanding, it is not really a well-developed theory. It applies to kind of simple settings, a particle moves in some potential, but applying it to quantum field theory or to quantum gravity, I don't think it is at that stage yet.
If something could come from nothing, then why doesn't this happen all the time? Why don't tigers just appear in our living room?
In quantum mechanics, many things are possible that are not possible in classical physics. And indeed, you can have, in principle, you can have very strange things happening, like objects coming out of thin air. However, there are some rules, and these rules are conservation laws. So energy conservation is always enforced. For example, you cannot have a tiger appear out of in the vacuum, right? Because tiger has some mass, some energy. But if you have a lump of matter, in principle, it can turn into tiger. And quantum mechanics will not tell you that this is absolutely impossible, but if you try to calculate the probability of this happening, it will be pretty low. On the other hand, in micro world, when you collide particles like they do at the Large Hadron Collider, you collide two particles and they turn into all sorts of things. They turn into other particles, or you can collide two protons and they turn into a cascade of a huge number of other particles. So on the microscopic scale, such processes do occur. And if you think of the quantum creation of the universe, it is a tiny microscopic universe, right, that has to pop out of nothing. If you calculate the probability of this happening, I should say that conceptually this probability, interpreting this probability is a little difficult, but still, if you do the calculation, you find that it is far more probable than having a tiger materialize in front of you.
Once a small universe nucleates, it is thought to undergo inflation. But as Vilenkin pointed out in the early 1980s, this has a mind-blowing implication for the large-scale structure of reality. It all has to do with how inflation ends.
It happens through bubble nucleation. So it is like boiling of water. A tiny bubble of our vacuum, like the one we live in, pops out in this expanding, inflating universe, and it starts to grow. And this bubble nucleation is also a random quantum process. It happens at different points randomly. And so you will have, after a while, this inflating space sprinkled with these different bubbles. The bubbles that formed earlier are big, the bubbles that are just forming are tiny. And as I said, the bubbles grow, but they very rarely collide because the space between them is expanding even faster. We cannot really travel to other bubbles because the boundaries of the bubbles are expanding so fast. They expand at the speed approaching the speed of light. So no matter how fast we travel, we will not reach the boundaries. So for all practical purposes, we live in a self-contained bubble universe. And an unlimited number of such bubble universes will be formed in the course of inflation. So that is why it is called eternal inflation. Inflation never ends in the entire universe. It ended in our part of the universe, and this is what we call our Big Bang, when this energy of the vacuum went to ignite a fireball of particles, and that was our local Big Bang in our bubble. But countless Big Bangs happened before it, in other bubbles, and will happen after it.
Many textbooks claim that inflation happens after the Big Bang. But when we spoke to Alan Guth, the father of inflation, in episode 4 of this series, he claimed that it might be better to think of inflation happening before the Big Bang.
In the early interpretation, Big Bang was kind of a singularity, where if you take the simplest cosmological models and continue them back in time, you find to a point where the energy density and temperature become infinite. And it's simply the point where the mathematics of the theory breaks down. You cannot go any further, and so that's where you stop. The meaning I use the term Big Bang in is the beginning of the standard hot cosmological evolution. So when the universe has very high temperature, very high density, is rapidly expanding, that's the Big Bang. Before that, according to present views, we have inflation. And now, Big Bang, the term is sometimes applied to initial singularity, if you want to consider one. But in fact, I think singularity is not a useful thing to have in a physical theory, because you want your mathematics to work, you don't want it to break down. What happened before the Big Bang? Inflation. What happened before inflation? And even no matter what you say, you can keep asking what happened before that. So creation from nothing kind of seems to be the only thing that stops this infinite regress. When I had the idea that the inflation is eternal, I went to see Alan Guth and tell him about this, and he actually fell asleep. So, I should say that now he's a great enthusiast of eternal inflation. When I got to know Alan better, I discovered, first of all, I discovered that he's a pretty sleepy fellow. He comes to seminars regularly, and he regularly falls asleep a few minutes after the seminar begins. In most cases, sometimes he actually stays awake, but these are exceptions. But then, no matter what, in the end, Alan wakes up and asks most penetrating questions about what was said in the seminar. And if I knew his supernatural natural abilities, I would continue telling him about my idea, but I quickly retired.
Many have claimed that, as other bubble universes cannot be directly observed, the multiverse is not science. In episode 4, we talked about the possibility of detecting signatures of bubble collisions in the cosmic microwave background. But Vilenkin and his collaborators have recently worked on a new proposal for testing the multiverse.
This multiverse picture, there is not just one type of bubbles. There is string theory, for example, predicts an enormous number of possible types of vacua. And all these, with each vacuum comes a corresponding type of bubble, which can be filled with that vacuum. And in the course of eternal inflation, all these vacuum states will be populated, so you'll have bubbles within bubbles within bubbles.
When inflation was going on in our region of space, bubbles of different vacua popped out and expanded.
When we worked on this idea, we thought, okay, what is going to happen to these bubbles when inflation ends? And the answer is that they will, instead of expanding, they will start contracting and they will collapse. They will form black holes. And we've calculated the mass distribution of these black holes, so there is a very uniquely defined distribution of masses. And for one thing, these black holes are interesting because they may explain, say, the origin of supermassive black holes that we observe in galactic centers. But also, if we really detect black holes with this predicted mass distribution, that would be evidence for the multiverse, that we indeed had this period where bubbles were nucleating. And so these are basically failed bubbles, these black holes. So these are direct tests. If we are lucky enough, we will be able to observe these things. But also there are indirect tests possible, where the idea is that if you have indeed this bubbles with variety of physical properties, some people noted that this may explain fine-tuning, observed fine-tuning of the constants of nature, because obviously we can live only in those bubbles which are suitable for life. But you can turn this around and make it a testable prediction. We can say, okay, if we have a theory of this multiverse, can we try to predict what kind of bubble we are most likely to inhabit? And in particular, what values the constants of nature, like gravitational constant or electron charge or whatever other parameters will have. This prediction was actually successful for one constant, which is the cosmological constant, or the vacuum energy density, or it is sometimes called dark energy. There was a great problem related to this parameter, which is that particle physics models naturally predict a huge value for this cosmological constant. And that would cause the universe to inflate at a tremendous rate, which we obviously don't observe. So the problem was why the vacuum energy is so small. if you calculate the vacuum energy, this large value comes from quantum fluctuations due to different fields. Like, for example, photons contribute positively to vacuum energy, and electrons, being fermions, contribute negatively. So in principle, you could imagine that different contributions will cancel out, but that would require cancellation up to 120 points, decimal points. So that would be a tremendous fine-tuning. However, if you have a huge multiverse with a very large number of different vacuum types, in most of these of the bubbles, you will have cosmological constant very large, and there will be no observers there. But in some very kind of rare bubbles, just by chance, you will have a small value, and that's where the observers will be. Now you can try to figure out what value we are likely to observe. Steven Weinberg was the first kind of to find the bounds. He found the bounds if the figured that if the cosmological constant is bigger than some certain value, then the repulsive force due to it is too large to allow galaxies to form. So that obviously will not be a populated type of universe. But the next step was to figure out, okay, this is where we don't live, right? So this is not really a useful prediction, but you can try to calculate where we are most likely to live. And that's in those bubbles where the cosmological constant does not start dominating before galaxies are formed, right? So it allows galaxies to form. And then you have a large number of galaxies. After that, cosmological constant can dominate without damage. And that predicts a value, or a range of values rather, which at the time when the prediction was made, people paid little attention to it because entropic arguments were in disrepute, I think. And then the value actually pretty close to in the predicted range was actually observed. It came as a shock to most physicists when the entropically predicted value of the cosmological constant was actually observed. And this changed many minds. So no other plausible explanations for the observed value of the cosmological constant have been found. So this may be our first indication that there is indeed a huge multiverse out there.
If the amount of dark energy in the universe is delicately fine-tuned for life, the multiverse can explain why. We have to live in a part of the multiverse that permits life. But a recent study has suggested that dark energy could be many times larger than the observed value without threatening life. Furthermore, they claim that this puts pressure on the multiverse as an explanation.
I think they somewhat exaggerated that. So the initial prediction, when you calculate the probability distribution, that calculation was actually pretty rude. Basically, the probability of finding a certain value of cosmological constant was identified with the fraction of matter that clusters in galaxy. So in galaxies. So if you have cosmological constant large enough to make, say, most of the matter to avoid clustering in galaxies, and only a few galaxies are formed, then the probability of such a universe is low. And if most matter is in galaxies, then the probability is high. And when you calculate the probability distribution using this, you find that it is pretty broad. And the observed value is on the low side of the distribution, but within the 95% range. So what they did more realistic calculation using numerical simulation of the universe, and they found that it is somewhat broader than, but not, in my view, not dramatically broader than analytic calculations did. But the main point is not that I want to make. The main point is that this model is, as I said, it is rather primitive. And for example, it doesn't consider differences between galaxies. So if the cosmological constant is large, for example, then it starts dominating early. And this means that galaxies also must form early. Any galaxies that you form will form earlier than galaxies in our version of the universe. Earlier means density is higher. So those galaxies will be denser. And stars will run into one another more often. And what's more important, supernovae will explode closer to us, right? Because the density of stars will be higher. And in the last few months, there appeared a paper where, I don't remember the names, there were 4 Japanese authors. They did a simulation, but now including this effect of supernovae. And with some realistic assumptions about how close you can afford to have a supernova to you without causing a great extinction. And they found that as a result, the probability distribution changes in such a way that we happen to be just in the middle of the distribution. So I think there is no big problem there.
While eternal inflation may be possible to probe experimentally, is there any prospect for evidence of tunneling from nothing?
The mathematics of this proposal gives you a probability distribution for initial states. So you can say what kind of state the universe is most likely to appear in. So it will be very small, filled with this high energy vacuum, what kind of fluctuations it will have, and so forth. The problem is that after that, you have this eternal inflation with bubbles and so forth. So the universe forgets its initial state. So you have tunnelings from one bubble to another, and so it's kind of a process where the initial state is completely erased, and that's why it's very hard to test. So far, nobody really figured out how it can be tested.
The universe could be closed like a sphere, or negatively curved like a saddle, or have no curvature like a flat plane. One thing tunneling from nothing does suggest is the shape of the universe.
The universe in this picture has to be closed because an open universe is infinite, and the probability for an infinite fluctuation is exactly 0.
So, but we observe the universe to be flat. Is that right?
Geometrically, yes, it's flat with a very high accuracy.
So how do you make that? Isn't a closed universe curved?
Sure. The universe is closed, and when it appears, it's like a three-dimensional sphere of extremely small radius. But then it inflates, and inflation makes it huge. So we see only a small portion of this universe, and it appears flat to us.
The tunneling from nothing proposal requires that the laws of physics exist platonically independent of the universe. One reaction has been that this cannot be, as laws are just descriptions of how objects behave and have no causal powers.
People who say that laws are mere descriptions, I don't know where they get this knowledge. It seems to me that the laws may well have some Platonic existence.
And do you have any thoughts on why the laws are what they are? Any ideas about that, or they're just a given?
I wish I had, but it's certainly the question that suggests itself. And the only attempt to address it was made, which I know, was made by Max Tegmark, who suggested that even bigger multiverse. He said that, okay, maybe all possible mathematical structures are somehow realized. I think this idea has some problems. Like, for example, there are many more complicated mathematical structures than simple ones, and the laws we observe have certain simplicity to them, and Einstein said beauty. So this seems to be a different selection criterion from just a random pick in the huge set of mathematical structures. But the bottom line is that we have no idea where the laws of physics come from.
A frequent problem that has been raised in the context of a multiverse is that of a Boltzman brain. If universes can spontaneously appear, why not just a brain? And if such brains dominated the multiverse, then why aren't we one of them?
Well, in the multiverse you have these bubbles nucleating, which are populated by observers like us, and you can also have these freak observers that fluctuate out of vacuum and or isolated disembodied brains, as people suggest, which have the same perceptions as we have. Once you have a specific model of the multiverse, you can figure out which are more probable. You can compare their numbers, and if your model predicts that predominantly the observers are Boltzmann brains, that model is, I would say, ruled out by observations. Maybe not ruled out by observations, but I think this model is unsatisfactory. But there is a criterion which you can figure out, and there are quite a few multiverse models which do satisfy the criterion, but that ordinary observers dominate over Boltzmann brains. So I don't think it is an unsurmountable problem. It is just a condition that needs to be satisfied.
In one of our previous episodes, we discussed the no-boundary proposal of Hartle and Hawking. How do these proposals differ from one another?
So the two proposals are similar in spirit, but mathematically they are rather different. And the predicted initial conditions for the universe are also rather different. In the tunneling proposal, the prediction is that the universe appears filled with the very high energy vacuum, and it has initially very small size. Because these things are related. The high energy vacuum corresponds to small size of the universe. The Hartle-Hawking proposal, on the contrary, says that the universe should appear filled with very low energy vacuum and have a very large size. The larger the initial size, the more probable it is. I find this rather counterintuitive, but on the other hand, things do not have to be intuitive with quantum gravity.
While inflation is the mainstream view of cosmologists, it does have its critics. And one of the most prominent of these is Neil Turok. He and his colleagues recently took aim at Vielnkin's tunneling from nothing proposal.
They claimed that this thing doesn't work, and that basically if you look at other particles other than just gravity and this field that is responsible for inflation, there are huge instabilities, that somehow these particles are created in huge numbers, and so the model predicts various disasters which we don't observe happening. And they claimed that this applies both to my proposal of tunneling from nothing and to the ideas of Hartle and Hawking, which were in a similar vein. So there was now a stimulus to re-examine these ideas, and I actually wrote a paper with Masaki Yamada here at Tufts, where we show that these things don't really happen, but this required a better understanding of mathematics of the model, and so we felt that we made some progress.
In 2003, Arvind Borde, Alan Guth, and Alex Vilenkin published a theorem, often known as the BGV theorem, which implies inflation must have a beginning. But does that mean that the universe as a whole had a beginning?
Theorem proves that inflation must have a beginning, right? The universe as a whole, the theorem doesn't say that. It says that the expansion of the universe must have a beginning, right? So, but it opens the door somewhat for alternatives.
One alternative that would circumvent the BGV theorem is a universe that contracted before it expanded. While many cosmologists we've interviewed find this a plausible option, Alex Vilenkin takes the opposite view.
Strictly speaking, the theorem allows the universe which is contracting from infinite size, for example, and then bounces and re-expands. This excludes the model of eternal inflation to the past. So the question that the theorem answers clearly is that inflation may be eternal to the future, but cannot be eternal to the past. There may be problems with contracting universes because basically contracting universes are highly unstable. If you have, for example, the galaxies are formed by gravitational instability. You have small overdensity and attracts matter and it grows. In flat space, it grows faster than an expanding universe. When the universe expands, it slows down all these instabilities. But in contracting universe, it grows catastrophically. So if you have some inhomogeneities in this contracting universe, they would grow out of hand. For example, if you have bubble forming, all these bubbles, instead of being driven away from one another, they will be driven towards one another. And so the whole thing will fill up with bubbles and inflation will end. But strictly speaking, it is allowed.
One of the great mysteries of cosmology is why did the Big Bang have such a low entropy condition?
Well, entropy is an extensive quantity. It's proportional to the volume. And the very small universe will necessarily have a very low entropy. But also it is filled with vacuum, and that is also the lowest entropy that you can have is the vacuum.
While Alex Vilenkin's picture of multiple Big Bangs is a radical one, many of his critics propose a cyclic model instead, which also has many Big Bangs. It seems there are very few, if any, cosmologists proposing the standard picture of a single Big Bang.
If you call standard what is called the standard Big Bang cosmology, which was a hot Big Bang, right? You start with a very hot, dense universe, and which begins at singularity. So that picture, I don't think anybody believes.
In eternal inflation, there is thought to be an infinite number of infinitely large bubble universes. But some have said that infinity cannot exist in the real world.
These bubble universes that form in the course of eternal inflation, these bubble universes, if you look at them from outside, they are spherical bubbles which expand. So at any given time, they are finite, but they grow indefinitely to arbitrarily large size. But then if you look at them from the inside, suppose you're an inhabitant of these universes, the geometry of them is very interesting, because in their interior, these bubbles are infinite spaces of negative curvature. How an infinite space can fit into finite space? This is because the finite inflating total universe grows exponentially, becomes exponentially large, and kind of infinity of space and time mixed together in an interesting way. So it's hard to explain in words, but my point is that these bubble universes are infinite from inside, and this is a mathematical fact. You could say, okay, maybe the entire space of the bubble is not in existence, at any finite moment. But I don't think that you can really meaningfully make claims like that, simply because in these inflating universes, different points in the space-time are not causally related. So whether or not the universe is infinite at this moment of time, you have to define what you call time, and there is no unique definition, because you cannot synchronize clocks in eternally inflating universe. Georg Cantor developed a theory of infinite sets, and he defined sets of different level of infinity. So you can have like one infinity bigger than another infinity. So mathematicians, at least some of them, some well-known ones, deal with infinities without fear.
Until a way to experimentally test the tunneling from nothing proposal is found, we may never know if it's right or wrong. But the fact there are still papers being published about it more than 30 years after it was proposed shows this idea has much staying power. So where do we go from here?
With the tunneling from nothing, I think now we seem to have entered a very stimulating period where, stirred by these papers by Turok and Lenners, I work with my collaborators here, and Hartle and his collaborators also kind of were spurred to activity. So I think at least there were some issues with mathematical formulation of these proposals which required clarification, and I think we are working on that now. I like the results that we get. That we think that we clarified a great deal about how mathematics of the proposal works. It would be good to have progress in quantum gravity. That that would provide another stimulus for the field. As for early universe cosmology, there are many things that one should be looking for, including dark matter, and there are some anomalies seen in the cosmic microwave background which kind of called for an explanation. They may be just flukes, but they look suspiciously kind of persistent. So it would be good to explain those. And maybe I could add one of my other favorite subjects, which is cosmic strings. It's the progress in early universe cosmology is closely related to progress in elementary particle physics at high energies. And we are coming to a point where building bigger and bigger accelerators becomes problematic, right? Because already we have an accelerator which is 30 kilometers in size. How much bigger can you get? So it would be good to find some other ways to investigate high energy physics. And one of the ideas is that in the early universe, of course, at early times, tremendous energies were reached, tremendous temperatures. And the idea is that as the universe cools down from this extremely high temperature, it can go through a series of phase transitions. And as a result of these phase transitions, the defects like cosmic strings or monopoles or domain walls can form. And cosmic strings appear to be the most interesting of these defects. They are kind of lines of concentrated energy, and they can produce a variety of observational effects. So observers are well aware of the possibility of cosmic strings existing, and for example, they can produce gravitational waves and some electromagnetic phenomena. So if cosmic strings are discovered, we are going to learn a great deal about high energy physics that we cannot learn at energies that we cannot even hope to get in accelerators.
As astronomers look out into the cosmos, one can only hope that new phenomena like cosmic streams or primordial gravitational waves might be discovered. If they are, they may be the keys that could unlock the mystery of our cosmic origin.